Everybody, in the last class we looked at 5 variable Karnaugh map based simplification and also for inter-variable map based simplification. Okay. So, in this particular class we shall look at QM algorithm, Quine-McClusky algorithm, which is also useful for simplification purpose, and we shall look into its important steps, that is finding prime implicants, finding essential prime implicants, and from that forming a minimal set, and also use of don't care in QM method. So, the QM algorithm, the steps, important steps are: first we shall look at getting the prime implicants. Implicants are the product terms. When we say prime implicants, then these are the product terms which cannot be combined with any other product term. So, that means prime implicants are having this number of literals for the mean terms it covers. Okay. This is cannot be further grouped with other product term, and then from that finding essential prime implicants to cover all the mean terms of a truth table, and then from these findings getting a minimal set to represent the given function. So, these are the different steps, and we take note of that finding this prime implicant. This goes through a iterative process, for which a computer based approach or algorithm or programs are available or people write, and for large number of variable minimization of large number of variables, these the corresponding functions, it is very useful. Okay. So, to understand how it works, let us look at one example. The example is very simple. It is a 4 variable example. So, we shall later compare with Karnaugh based simplification also, how it works and all. So, this is having mean terms 0, 1, 2, 3, 10, 11, 12, 13 and 14. Okay. So, the first step, as I said, is to find prime implicants, and to get prime implicants it goes through, as I said, iterative process. So, let us first look at the stage 1 of the process. So, in the stage 1 of the process, what we are doing? We do a grouping of the mean terms in terms of input variable combinations. So, input variable combinations, the first group that we are having is those mean terms where no 1 is present in the input combination. If such mean term exists, it will be, there will be such a group formed, otherwise it will not be there. So, since in this example 0 is a mean term that is present, right. So, 0 0 0 0 this combination is present, so it is there, okay. And there is only such one such possibility that no 1 is present. So, that is why there is only one member in this particular group. Okay. So, next we form another group with those inputs, for those mean terms where the inputs are having only 1 1 in their combination. So, 0 0 0 1 this is present. So, this is there, 0 0 1 0. So, it is there. So, the other input combination where there is only 1 is 0 1 0 0, that is 4, but 4 is not a mean term in this example. So, 4 is not present. So, 0 1 0 0 is not present. The other option is 8. Okay. So, 1 0 0 0. So, that is also 0 over here, that is not a mean term. Okay. 8 is not here in this particular example. So, it is also not member. So, wherever it is a mean term is present, then corresponding value it is made available in this particular group. Okay. Now, next group we will be forming, as we understand, that is why I said it is a iterative process in that sense also, in the way we are forming the groups. So, 2 1s will be present. So, 2 1s are present for mean terms which is 3, 10 and 12. This way you can see 3, this is there, right. Other 2 1s that is present here is 5, but 5 is 0. So, it is not a member. Okay. So, we have to consider the 1 that are present. So, 3, 10, 12 are there. So, similarly 3 1s are present. Okay. Next group, that is 11, 13, 14, and last all 4 1s are present. If 15 is a member, if 15 is a mean term, then it will be there. So, it is for 4 variable cases. So, 5 variable, 6 variable case, then there will be more such groups with 4 variable combinations, 5 with combinations of 4 ones, with combination of 5 ones, with combination of 6 ones, and so on and so forth. It will continue. Is it fine? So, this is by this we get the stage 1, the first arrangement of this QM algorithm, and in this case other than what has been mentioned here, since the way the min terms are appearing, their order of appearance has changed. So, we just write the corresponding decimal value alongside in the right hand side to make sure that all the min term has been properly included from here. So, no min term should be left, so that it does not go out of our attention. So, we are also writing it in this manner. Okay. So, from that we go to stage 2. So, in the stage 2 what we do? We form groups again the way we had done before, but in a little bit different manner. So, we take adjacent blocks. Why adjacent blocks? We shall tell later. So, adjacent blocks of stage 1, and then we see among the members there, the input combinations, the min terms, where they are just differing by 1 position. Okay. So, we form a pair of them like 0 0 0 0 and 0 0 0 1. Input combination is just changing the D position 0 to 1 and ABC remaining same as 0, all 0. So, that is only one change is there. Okay. So, we take up this as a member that goes into the next stage 2 first block. Okay. And the place where D is changing, we put the variable that is that position where the value is changing. So, that we put as a dash. Dash means what is the physical significance of it? That whether D is 0 or 1, dash is kind of do not care, that a min term is produced. That means, ABC is 0 0 0, D is 0 or 1, okay. There are min terms. So, 2 min terms are there for D is equal to 0, ABC remaining 0, all remaining 0, and D being 1, ABC all remaining 0. So, that is the physical significance or meaning of it. Okay. So, similarly 0 and 2 we can see we can combine because only C position is changing. So, 0 2 is the next member of the block. So, that is these are the only possibilities. Now, can this first block be combined with block 3? For this particular consideration, that is only one position will be changing, we cannot, because we know in the first block there was only no 0, and in this particular block 2 ones are there. So, they are differing at least by 2 positions, is not it? These 2 positions are they are differing. So, this because of which you just cannot. So, this block, so subsequent blocks are differing at least by 2 positions, not 1 position. So, they cannot be grouped with this particular first block. Okay. So, we are not considering them, right. Now, we look at whether this block and this block can be combined and what are the different possible ways. And for that we see this 1 can be combined with 3, because A, B and D are having values 0, 0, 1 respectively, 0, 0, 1 respectively. Only C is changing from 0 to 1 over here. So, we write 0, 0 dash 1 in this particular case. Again C, this physical significance is the same, that for A, B and D 0, 0, 1 respectively, C whether 0 or 1, there are 2 min terms available in the truth table. Okay. So, similarly, okay, this 2 and 3 can be combined, 2 and 10 can be combined. So, this is what we can see. Can 1 and 3 be combined? 1 and 10 be combined? So, this is 1 and this is 10, right. So, we see this is 0 and 1 they are changing, 0 0 the remaining constant, again 0 and 1 it is changing, and 1 and 0 is changing. So, more than one position it is changing. Is it all right? So, for which we cannot have 1 and 10 combining the way we have seen that only one position that is changing, in place of that we shall put a dash, rest of the values will remain same. Okay. So, next we see that this block and the other block, okay, how it can be combined, only as I said adjacent blocks are required. So, this 3 and 11, so 0 0 1 1 and this is 1 0 1 1, only one value is changing. So, it can be combined. So, the first value that is there, which that position is only changing. So, that will be a dash and rest of the values are 0 1 1. Okay. So, similarly, if we keep examining or write an appropriate code, so it will be having this particular groups formed. Okay. Similarly, for combining these two blocks in stage 1 of stage 1, where only one position is differing, we have 11 15, 13 15, 14 15, these are the combinations formed, and accordingly their representation is mentioned here. Okay. Now, one more job is left in stage 2. So, when you do the combination, we look at where every member of stage 1 has been part of a group of stage 2. Okay. If it is, then we put a tick mark against it. If it is not, we keep it unticked, that it could not be combined. Okay. For a particular function or a truth table, it might be so possible that it is not able to combine, because it is not changing in one position. Okay. So, it will not be ticked. So, it will just remain there. So, what is its significance? We shall discuss little later. So, we have completed stage 2. As I said, it is an iterative process. So, we move to stage 3, and what we will do in stage 3? We shall look at adjacent blocks of stage 2, right, and we shall see whether they can be combined following the same principle, that is, their two members are differing only in one position. Okay. So, let us see whether it is possible or not. So, 0 1 0 0 0 dash and 1 3 0 0 1 0 0 dash 1, are they differing in one position, only one position? No. 0 0 0 0, this is fine, 0 and dash and 1. Okay. So, because of which we cannot combine these two, because it is differing in two position. Okay. Now, 0 0 0 dash and 0 0 1 dash, can these two be combined? Yes. Why? First two are 0 0, D position is dash, only C position is changing, in one case it is 0, in the other case it is 1. So, this is a candidate. So, corresponding term will be 0 0, dash was already there. So, this 0 1, now a dash is coming over here, and the term corresponding term is 0 1 2 3. So, this is going as in the stage 3, is it fine? So, 0 1 is going in the stage 3, 2 3 is going in the stage 3, we can put tick mark against them, right. Next, 0 2 and 1 3 can be combined, right. Similarly, if we look at examine 0 1 and 2 10, whether it can be combined or not, we see that it is differing in many places. So, 0 dash is differing, 0 0 is not differing, 0 1 is differing and dash 0 is differing. So, 3 places it is differing. So, they cannot be combined. Okay. So, once this part is done, between these two adjacent blocks, we shall look at these two blocks, and between these two blocks we can see that 2 10 3 11, 2 10 3 11 they can be combined, and rest of the combinations are not possible, because it is differing more than one places. Okay. And 2 10 3 11 dash 0 1 0 and dash 0 1 1. So, 0 1 is and dash is same, 0 and 1, this is only changing. So, that is a dash over here which is coming here. Okay. And finally, between these two blocks, okay. So, these are the different possibilities. If we just examine the same way, we shall get it that 10 11 14 15, okay, and 12 13 14 15 they are there, and the corresponding terms are this. Okay. So, 12, 13, 14, 15, if you just take an example say here and 14. So, 1 1 0 dash and 1 1 1 dash. So, 0 and 1 that is only differing this position and this position. So, we put a dash. Okay. So, we can examine one member against the other and we can do it, and if we are writing a code, then you can write a code for that. Okay. So, in doing that we see that 0 1, 2 3, 2 10, 3 11, 14 15, 12 13, all the members have found a place in the next block. So, each one of them is ticked. Is it okay? Now, finally, when we have reached stage 3, we shall look at what? We shall look at whether we can move to stage 4 by combining this, right. So, if that is where they differ only in one place, is there in such case? So, if you look at 0 1 2 3 and 2 10 3 11. So, if you compare these two, okay. So, 0 and dash it is differing, 0 0 not differing, dash and 1 it is differing, dash dash it is not differing. So, two places it is differing, 0 dash this position, A position and C position. So, they cannot be combined. Okay. So, either 0 2 1 3 and 2 10 3 11 can be combined. If we examine this and this, okay, 0 dash A position it is differing, B position not differing, C position it is differing, D position not differing. Okay. So, it is differing here and it is differing here, again two positions it is differing. So, it cannot be further combined, only one position it should change to become a member of a group in the next stage. So, similarly, over here if you look at 2 10 3 11 and 10 11 14 15, whether they can be combined, just for example. So, this is different, A position is different, B position is different, C and D are same, okay. But A and B are different. So, because of two positions differing, again they cannot be further combined. So, we can combine, examine each one of them and see that none of these can go to the next level, and because of which there is no stage 4 and also none of this member over here is ticked. Okay. Now, each unticked term, now we understand the significance of this unticked term. So, each unticked term is a member, okay, to contribute to prime implicant generation. So, each unticked term will generate a prime implicant. Okay. So, here all this will be coming from this stage, but if any previous stage there is an unticked term, okay, so that has to be brought forward in the final prime implicant that we get out of this exercise. Okay. So, in this example, so these are the 4 prime mutually exclusive, because you see 10 11 14 15 and 10 14 11 15 they are the same, okay, they mean the same. So, that is 1 dash 1 dash. So, they are not essentially different. So, basically these are the 4 terms that we get which will contribute to the prime implicant formation. Okay. So, all the 3 stages combined together, it would look something like this, the one that you see, right. Earlier we had shown it at a separate manner, but when you work it out, you can just keep on adding tables and columns and all till it converges. The convergence is guaranteed because you can see in each of these cases the number of these blocks, the groups are coming down from stage 1 to stage 2, stage 3, it was 1, 2, 3, 4, 5 here, 4 here, 3 here, right. So, that way the the extreme scenario will be that all are dash, A, B, C, D, E all are dash, okay. That means, it does not matter, the output is 1. So, y is equal to 1. Okay. So, that is one extreme case that you can see that irrespective of any change in the value. So, all input becomes kind of do not care, any value whether it is 0 1, any combination output is 1. Okay. So, that is the kind of meaning one can bring out for such cases, but it converges, it cannot go beyond that. Otherwise, the convergence we had seen the way that after stage 3 it cannot be further grouped. So, it does not go to stage 4. Okay. So, this is how it will pan out. So, this is the PI table, this is called the PI table, and the corresponding terms that we get, this 0 0 dash dash and other terms. So, the way we define it, wherever there is a 0, we write is as A prime corresponds to A and corresponds to B. So, 0, so it is B prime. Okay. So, the corresponding product term representing this prime implicant is A prime B prime, and the mean terms that is covered by it is 0 1 2 3. So, B C, B is remaining constant with 0 and C is remaining constant with 1. So, B prime C is the corresponding prime implicant. A is remaining constant with 1 and C is remaining constant with 1. So, AC is also the AC is the corresponding prime implicant. Finally, 1 A for A and B. So, this is AB is the prime implicant. At the mean terms that are covered, we can see at this side by side it is mentioned. Okay. This is understood how we are getting. So, the first step is getting prime implicants and through a prime implicant table through an iterative process the way we have described so far, and for this example we arrive at this. Now, we have got the prime implicants, we have got the product terms. If we just sum them up algebraically, we will get y which is correct. I mean, there is nothing, but whether it is giving you a minimal set or not, it is not yet ascertained. Okay. To ascertain that, we shall look at next stage, which is next step, which is called finding essential prime implicants. What does it do? In essential prime implicant table, we are looking at the requirement of the coverage of all the mean terms by the prime implicants that we have got in the previous step, okay, through the prime implicant table. So, the mean terms that need to be covered for this specific example as 0 1 2 3, 0 1 2 3, 10 11 12 14, that is the one that you can see, right. And then we write the corresponding prime implicants that we have got and what are the mean terms that are being covered by them. So, the coverage by A prime B prime is 0 1 2 3, B prime C is 2 3 10 11, AC is 10 11 14 15 and AB is 12 13 14 15. Is it fine? So, this is the way we get the essential prime implicant table, right. So, these corresponding tick marks are there. Now, when we look at this essential prime implicant table and the corresponding these prime implicant, prime is a essential prime implicant. So, A prime B prime is a essential prime implicant, is an essential prime implicant. Understand this point? Because if we remove, if it is not considered, then 0 and 1 prime mean terms will not be covered. The same way 12 and 13, okay, is covered only by AB and not by any other prime implicants. So, AB is also an essential prime implicant. So, this is there. Now, when A prime B prime and AB these are included, these need to be considered in the SOP form, right. So, what is the mean terms that remain yet to be covered? They are 10 and 11. They are 10 and 11 because A prime B prime and AB are covering 0 1 2 3 12 13 14 15. So, 10 to cover 10 11 we have got two terms with in a similar complexity if we consider that the inputs are available in complement and uncomplemented form. So, one is B prime C, another is AC. Okay. So, one is covering 10 11 as well as 2 3, another is covering 10 11 as well as 14 15. So, we can take either of them, okay, and we can get one set of essential prime implicant using this, I mean a minimal set like this, another minimal set like this. Okay. So, this is the two possibilities. These are the two solutions that we can get out, I mean two possible solutions, okay, with similar complexity from the QM algorithm for the given example. And we can examine whether this is okay or not by the K-map based simplification that we are already familiar with. So, the mean terms if we map it in the K-map, this is how it would look like, okay. And one group A prime B prime comes over here, AB comes over there, Okay. And the remaining two ones that need to be covered, this is 10, 11 in the Karnaugh map, you know, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So, this is the 10, 11. So, 10, 11 can be grouped to like this, this particular one or this one, the way it has been seen. Okay. Two possibilities are there. So, in one case we will get AC, another case it will get P prime C. So, one of them need to be considered, so that 10, 11 remain covered and A prime, B prime and AB must necessarily be present. Okay. So, how we find the QM algorithm based simplified expression if there is a do not care case. So, do not care means at the input side we do not care. So, we know these x by which we had presented them in the Karnaugh map. So, what we do, the method is simple, these do not care we considered as min term in the generation of prime implicants. Okay. So, when you do that, there is a possibility of getting largest sized group, okay, and we exclude it when the coverage is required, okay, in the finding of min term coverage is required in the finding of essential prime implicant. This is what we do, okay, and by which we can ensure a minimized or simplified expression. So, we can take this example which is just a variation of the example that we had taken. So, 0, 1 is the do not care. Earlier we considered min term as 0, 1, 2, 3 up to 14, 15. Now, we are considering min terms are 2, 3 to 15 and 0, 1 are the do not care. So, in the first stage, as I said, 0, 1 will be considered as min term to find the prime implicant. So, the prime implicants that we had got in the previous example will be this one in this particular example as well. So, the prime implicants we shall get are this A prime, B prime, B prime C, AC and AB by the same method. Now, in this example, because 0, 1 is something which need not be covered, okay, it is do not care. So, 0, 1 is excluded, you see 0, 1 is not over here, we are starting from 2, 3, 2, 3, 10 to 15. Okay. So, accordingly it has been written, and what we see in this essential prime implicant formation that B prime C and AB between themselves 2, 3, 10, 11 and 12, 13, 14, 15 all the min terms are getting covered. Okay. So, the minimized expression we get is AB plus B prime C. So, this is what we do in case of QM algorithm based this method. Okay. And we are not discussing a similar thing for POS, but we have already noted that from the dual circuit thing. So, we can find F prime, okay, for this example. So, we can get F prime where this will be 1 and this will be 1 and rest of the things will be 0, by which we can get the expression. Okay. And then we take the complement, the dual of it means AND becomes or becomes AND, and the input outputs are complemented. So, F prime we have considered, so output becomes F, okay, and inputs will just get complemented, and then AND becomes or becomes AND means we get the POS representation. Okay. So, to conclude, QM algorithm based simplification first identifies prime implicants. These are the products terms which cannot be combined with any other product term. So, it represents a least number of literals, and essential prime implicants are the PI which together cover all the ones of the truth table, and a minimal set with essential prime implicant is arrived at for the function of getting the function final function output. Do not care conditions are included in finding prime implicants, but excluded in finding essential prime implicants for incompletely specified truth tables having do not care, and this is useful for computer based simplification of a Boolean expression. Thank you.